Good morning, everyone. So, as Julia mentioned, this is work that I'm doing as part of my PhD research project. I'm about halfway through, so it's very much a work in progress. So it's quite evident that we live in an urban age. Most of us live or work in cities, and the much touted fact is more than 50% of the global population now lives in cities, and in Europe and North America that figure is more 70 to 80%. And with ever-increasing population growth, cities are getting bigger and more numerous. And there are obviously many advantages for living in cities, but there are disadvantages too. Besides overcrowding and crime, cities are also concentrators of environmental impacts, and they are also prone to unique environmental conditions that make them particularly vulnerable to extreme events. Flooding in particular is a big issue. The density of both people and infrastructure in these urban areas escalates the devastation. And under future climate, these impacts are projected to get worse. There are going to be increases in the number and intensity of heavy precipitation events. But when we're talking about flooding, it's important to be aware of the different types of flooding. In cities, we are probably most familiar with urban flooding or fluvial flooding, which is where our drainage systems get overloaded by a particularly heavy precipitation event. However, it's fluvial flooding or flooding that we get from rivers that is the biggest problem for cities. Cities are generally located on rivers or in downstream parts of catchments, and they will receive all the downstream accumulated floodwater. So for my project, I'm aiming to examine the potential for ecosystem-based adaptation to climate change using natural infrastructure. Here, I refer to natural infrastructure as how we can use nature to provide the services that we would sometimes normally associate with built infrastructure, such as dams or dikes or other storage mechanisms. And one of the ways I aim to do that is by modeling and mapping the role of rural ecosystems, so upstream, in providing flood mitigation to the world's cities, and how that's going to change under future climate. So how am I going to do that? I began by dividing the parts of the landscape that store water, which we call natural infrastructure. So first of all, water bodies, then floodplains, wetlands, soil, and canopy, and then divided them into first brown infrastructure. Brown infrastructure would be your water bodies and floodplains, and those are generally functions of topography and are quite difficult for us to change or modify. The others, we're calling those green infrastructure, and we can increase or restore green infrastructure, and so they can be the focus of conservation or management issues. So to calculate the water storage capacity of these different components of the landscape, I'm using a model called WaterWorld. It's developed by my supervisor, Dr. Mark Mulligan. It's free and it's fairly easy to use, and it's quite sophisticated. It's essentially a hydrological modeling tool which can measure water balances, baseline water balances, at 1 kilometer or 1 hectare scale resolution. And as opposed to other hydrological modeling tools, all the data, all the inputs are already in the system. So you don't have to provide any of your own data, although you can if you want to. And as I said, it uses mostly global data sets. And one of the key things about it is that it can do scenarios, either for different types of land use change or climate scenarios, and I'll be showing you some of those. And so it's web-based, and it's fairly easy to use, but it is powerful. So for my project, I've been trialing a new component of WaterWorld to measure these natural infrastructure metrics, particularly the water storage capacities of floodplains, water bodies, wetlands, canopy, and soils. And I've just shown you some of the data sets that we use to capture those, and also to show we're measuring them at sort of cubic kilometer scales, and that there are some user-defined metrics here. So it's not particularly, there are some assumptions based in those, so it's not particularly precise, but it does give a good idea. So I'll show you some results. Oh, first of all, the cities that I was looking at. So we're trialing it out on 6 cities around the world. So Guayaquil in Ecuador, Bogota in Colombia, London, Nairobi in Kenya, Chennai in India, and Jakarta in Indonesia. So some results of those cities. So if you look at this bar graph, I've listed the city basins. So these are basins upstream of these cities, from the smallest basin to the largest. So the smallest is Nairobi, it's an upstream city, to Guayaquil. And the bars show how much water storage capacity of canopy soil, wetlands, floodplains, and water bodies. And as you can see, the largest basins have the largest water storage capacity. That shouldn't be a surprise. But what is interesting is that canopy and soil across the board seem to make up the majority of the water storage capacity, with floodplains next. And then some cities like Nairobi showing hardly any water bodies, and there tends to be very little in the way of wetlands. So those were showing the total water storage capacity. I've then taken the mean storage capacities to remove the effect of the basin size. And then what you can see is that Guayaquil still has the most water storage capacity, but then Chennai, even though it was a fairly small basin, it's actually showing quite a large amount of water storage capacity for its basin size. And I've also aggregated the water storage capacity into that green and brown storage. And what's interesting to notice here is that almost across the board, green storage is greater than brown storage. The exception is Chennai, which has more brown storage than green storage. What's probably more interesting is to look at the relative proportions of the green to brown. So if you look at Nairobi, Nairobi has 7 times more green storage than brown storage. This is interesting because the green storage is what can be modified or changed, but also developed on. So if that green storage is under threat and it's removed through development, then Nairobi could be in trouble from a lack of storage and therefore at risk from flooding. So what we also did is we looked at how much of the green storage is protected in some way. So on the left here, you can see that London, the upper London basin, has the most protected green storage at 34%. That includes areas like areas of outstanding natural beauty. But some basins, like the Guayaquil Basin, which is a massive area, only has 3.4% of its green storage is protected. And Chennai, none of it is. Chennai is an area which has quite a lot of monsoonal flooding. So I think that's quite interesting to flag up. Obviously, when we're talking about quite large geographical areas, it's good to see how that water storage is distributed spatially. So this is a map showing the London basin. So this is the Thames basin, the Wandle, and the Lee and Ravensbourne basin, and it's showing the areas upstream of London, and it's showing the areas of total storage capacity. So the areas of the green and yellow are showing areas of high total storage capacity. And this map shows areas which is showing which storage is dominant in each pixel. So you can see that the areas which had the highest total storage relate to the floodplains. So the floodplains, even though they're quite local, have the most storage capacity. Also thought this was quite interesting to see how soil storage was greater in the northwest part of the basin, where canopy storage was greater closest in and around London. So that's showing water storage capacity, but now we have to relate it to precipitation, how much rainfall actually comes into the system. Because if there's more rainfall than storage capacity, that's when we'll get runoff and risk of flooding. And then I'm interested to see how this is going to change with projections of climate change. So this can get a bit technical, but when we look at climate scenarios, the current way to look at it is through representative concentration pathways, RCPs. And basically, RCP 2.6 is the best case scenario, which I haven't actually included in my analysis because I think there's no ways we're going to achieve RCP 2.6. And then RCP 8.5 is the worst case scenario where we have emissions which continue increasing all the way to the next century. So this graph is showing how both water balance and rainfall is going to change under RCP 4.5. So sort of that's the best case scenario at the moment for my different cities. So you can see if we just start at the bottom here looking at rainfall, we can see that for pretty much all the cities, city basins, rainfall is projected to increase, except for Jakarta. But if we look at water balance, which is basically all the water inputs minus evapotranspiration, we can see that both Jakarta and London are going to have a negative water balance. And this is over an annual time step. So you might think, well, should we be worried about flooding in London then? If basically rainfall's only going to increase a little bit and go negative in total water balance. So I'll get back to that. But what we've done with this tool is we've related the incoming precipitation to the water storage capacity as a ratio. And if the incoming precipitation is greater than the storage, then we said that area is high risk, and if it's lower, then it's low risk. And then we've mapped how that's going to change under these different climate scenarios. So for RCP 4.5, this is a map showing the flood trajectory for the Thames Basin on an annual scale. So areas of red are where high-risk areas are going to increase, or like the dark green that we'd be interested in is where low-risk areas become high-risk areas. And you can see that pretty much for the London Basin on an annual time scale, it's mostly yellow. So basically, low risk is decreasing. So this is kind of showing that maybe we shouldn't be worried about flooding in London. If we look at RCP 8.5, the worst case scenario, yes, there's a slight increase in flood risk in the basin, but it still doesn't look particularly alarming. However, if we look at one of our other city basins, Guayaquil in Ecuador, for RCP 4.5, I would be pretty worried if I was living there. But as I said, these were showing on an annual time scale. When we looked at the seasonal time scale, this is for the London Basin, and we can see that this is showing rainfall, and you can see that rainfall for all the different climate scenarios and for the different sort of for the 2050s and for the 2070s, you can see that rainfall is actually going to increase substantially in the winter months, so particularly December, January, February, and March, April, May. So what this means is that we should be targeting our flood mitigation interventions quite seasonally for quite wetter winters and drier summers. So I haven't really shown you any particular solutions at the moment. We're still getting that, but hopefully I've shown how you can use a simple but sophisticated tool to indicate things like water balances, water storage capacities, and different climate scenarios for places all around the world, and how we've shown a novel way of indicating flood risk and how that can change under different climate scenarios, as well as land use scenarios eventually. And our next step will be to see how we can determine how much green infrastructure needs to be put in place, restored or maintained in these upstream areas to reduce flood risk and adapt to climate change. As I said, this is a work in progress, so we are very interested in finding stakeholders who are willing to engage with this work to help us determine how useful this is and how it could meet their needs. So if you're interested, and we'll also be running training sessions, workshops on the use of WaterWorld. So please get in touch with me if you're interested. Thank you.